So how in the world do we know what a star is made of when it's trillions upon trillions of miles away? I mean, we can't exactly go there and scoop up a sample, right? Well, the answer is one of the most elegant and honestly coolest ideas in all of science. It turns out every star broadcasts its own unique cosmic barcode, and it's hidden in its light. You've definitely seen this before, probably back in science class. You shine white light through a prism, and out comes this beautiful, perfect rainbow. A smooth, unbroken band of color. It's clean, it's simple, and it's what we all think a rainbow is supposed to look like. Yeah, you heard me right. The rainbow we get from our own sun is actually broken. The light that travels 93 million miles to get to us isn't a perfect, continuous spectrum at all. It's got pieces missing.
And this is it. This is what the German physicist Joseph von Fraunhofer saw way back in 1814. He used some really precise instruments to look at sunlight through a prism, and instead of a smooth rainbow, he saw this, a spectrum just riddled with hundreds of these mysterious, thin, dark lines. It was a huge puzzle that he had no way of explaining.
So, of course, this kicked off a massive scientific investigation. What in the universe could possibly be carving these lines into the sunlight? What was stealing these very specific colors before they reached us?
Well, it turns out the culprit was the sun itself. You see, the light from the sun's fiery core has to punch its way through the sun's own outer atmosphere, which is full of cooler gases. And these gases act like tiny little color filters, each one grabbing or absorbing its own favorite colors of light.
And that right there brings us to the most important point. The things doing the absorbing? They're atoms. And every single type of atom, whether it's hydrogen or helium or sodium, it leaves its own unique spectral fingerprint on any light that passes through it.
Okay, so here's the key idea. An atom can interact with light in two opposite ways. A cloud of cool gas will remove, or absorb, very specific colors from a rainbow passing through it. But if you take that exact same gas and heat it up until it glows, it will create or emit light of the exact same colors it used to absorb. It's really just two sides of the same coin. And look at this. This shows it perfectly for hydrogen. That top bar is its absorption spectrum. You can see the dark lines where it removed color. The bottom one is its emission spectrum. The bright lines are the colors it gives off when it's hot. They are perfect mirror images. The pattern is identical. This was a gigantic aha moment for scientists.
So why? Why do atoms do this? Why are they so picky about which colors they interact with? Well, to get that, we have to shrink way, way down and take a look at the bizarre quantum rules that run the show inside every single atom.
The central idea is this. Electrons buzzing around the nucleus of an atom aren't allowed to have just any random amount of energy. Nope, they are locked into very specific discrete energy levels. We say their energy is quantized, which is just a fancy way of saying it comes in distinct packets. The best way to think about it is like a ladder. An electron can be on the first rung, or it can jump to the second rung, or even the third. But it is physically impossible for that electron to just hover in the empty space between the rungs. It has to be on one rung or another. There's no in-between.
And this isn't just some cute analogy. This is literally how it works. This diagram here shows the actual energy ladder for a hydrogen atom. Each one of those lines is an allowed rung, where its electron can exist. All that space in between, that's forbidden territory.
So how does this whole ladder thing explain those missing colors? Well, it all comes down to a perfect little dance between particles of light, which are called photons, and these energy rungs. And here is the absolute key, and I'm quoting directly from our source material here. Energy of absorbed photons must match the energy difference between excitation states in the atom. What does that mean? It means it's all about a perfect energy match. For an electron to jump from a lower rung to a higher one, it needs to get hit by a photon that has the exact right amount of energy to bridge that gap. Not too much, not too little, perfect. Okay, so let's walk through it. Step 1. A photon with that perfect amount of energy comes along and smacks into an electron. Step 2. The electron gobbles up that photon's energy and uses it to leap up to a higher rung. But it's unstable up there. So step 3, almost instantly, the electron falls back down to its original, cozier rung, and as it does, it spits out an identical photon to the one it absorbed. And now, here's where it all connects back to the rainbow. A photon's energy is its color. They're the same thing. Photons of blue light are packed with more energy than photons of green light, which have more energy than photons of red light. So different-sized energy jumps on that ladder require different colors of light. And for anyone who loves the math,
Here's the equation that makes it all happen. Energy, that's the E, is directly tied to the wavelength of the light. That's the Greek letter lambda. All this really says is that a shorter wavelength, like blue light, means higher energy, and a longer wavelength, like red light, means lower energy. Simple as that.
We could even put some real numbers on this. A single photon of blue light is carrying about 3.1 electron volts of energy. A red one? Only about 1.77. So when a hydrogen atom absorbs that very specific shade of red light, it's because it needs exactly 1.77 electron volts of energy to make a particular jump on its ladder. It's incredibly precise.
Okay, let's pull back. We just went from a giant cosmic mystery all the way down into the weird quantum world of a single atom. Now for the payoff. Let's see how all of this unlocks the secrets of the entire universe.
So here's where it all comes together. Every element on the periodic table, hydrogen, helium, carbon, you name it, has a totally unique number of protons and electrons. This means each one has its own unique energy ladder. And if it has a unique ladder, it produces a unique pattern of spectral lines. It's a chemical barcode, and every single element has.
So now, when we point our telescopes at a star millions of light years away, we can catch its light, spread it out into a spectrum, and see all those dark lines carved into it. Then, it's just a matching game. We look for the familiar barcode patterns of the elements we know. It is cosmic detective work on the grandest scale imaginable.
And it works beautifully. By reading the sun's spectral barcode, we can clearly see the fingerprints of hydrogen, helium, carbon, nitrogen, sodium. The list goes on. And here's a fun fact. Helium was actually named after Helios, the Greek sun god, because it was first discovered by analyzing the sun's light years before we ever even found it here on Earth. How wild is that?
So you see, those mysterious dark lines that Fraunhofer saw weren't a mistake or a flaw in the rainbow. They were a code. And once we cracked that code, we unlocked the ability to do chemistry on stars that we could never ever hope to visit. It completely changed how we see the cosmos.
So we figured out how to read what the universe is made of. But these barcodes, they hold even more secrets. Because if a star is moving towards us or away from us, its entire barcode gets shifted a little bit. Kind of like how the sound of a siren changes as it passes you. So the next big question is, what else can these lines tell us? Can they reveal not just what the universe is made of, but where it's all going? I think the reading has just begun.